Welcome to our lecture of the flexible AC transmission system. Today we are going to discuss a new topic, that is voltage phase angle regulation, or in abbreviation we shall use the term phase angle VPR or PAR. So, our discussion will be based on the understanding of the PAR, that is the introduction, followed by the voltage and the phase angle regulation functioning, and the power flow of phase angle regulator, that is PAR, reactive and the real power loop of and the power flow, and the reactive power flow control. Then the transient stability improvement by PAR, that is same we have discussed for the series and shunt, and we continue with the also with this PAR, and the power angle oscillation also with the phase angle regulator. So, why we choose phase angle regulator? Essentially you know that sending end voltage, receiving end voltage by x into sine delta is the power sent through the transmission line. So, instead of you have advantage and disadvantage of both. Of course, you can increase the sending end power by changing the actually the voltage V1 or V2 or X that we have seen in case of the series compensation real power. But we can also do the same thing by changing the delay angle alpha, delay angle delta, and thus power can be enhanced or decreased as you wish by not touching other parameters like V1, V2 and X. The transmitted real power P and the reactive power line Q are the function of the transmission line impedance, the magnitude of the sending end and the receiving end voltage, and the phase angle between these voltages. So, now we shall deal with this part, that is phase angle. Already we have discussed the series compensation, which can be highly effective by means of the power flow in the line, as well as the improving the dynamic behavior of the transmission line of the power system. The series reactive compensation is generally highly effective for the power flow control, but is impractical or economically non viable or non economical for some applications. So, where you actually you have to increase the power rating of the devices, and you require to have different devices with a high power rating. Problem involves control of the real or reactive power flow in a mesh network. So, there actually you have to find it out where the maximum sag occurs, and you have to compensate that. Solution of this problem requires the control of the effective angle delta. It is not that V and X, you have to control the delta. Apart from the steady state voltage and the power control, the role of the modern load of this phase angle regulator with a fast electric control can also be extended to handle the dynamic system events like oscillation, falls, subsynchronous reactance, all those. As compared with the reactive compensator, voltage and the phase angle regulators brings a new element to the control dynamics event, and the capability of this power lines and is enhanced. So, it is one of the new member, and it shows a huge potential to increase the or effectively control the power handling capability of the transmission line. Now, what is the concept? The basic concept of the voltage angle regulator is addition of the appropriate phase angle. So, you got a delta, delta will be modified by delta plus sigma or minus sigma, that is what we wanted to do. Appropriate in phase or adequate quadrature component to the prevailing terminal voltage in order to change, increase or decrease the magnitude or the angle of the value is specified or desired. Thus, the voltage regulation could theoretically be achieved by a synchronous in phase voltage source with controlled amplitude plus minus delta V in the series with the AC system. An adjustable voltage is provided by means of the tap changing 3-phase auto transformer for the primary series injections or insertion of the transformer. We shall see this circuit here. So, this is the in phase voltage regulator. So, what happened? You have the actually step changing or auto transformer. So, from there you will tap this thing and ultimately you will add up a voltage in phase. So, what happens? The transmission capability increases, and same way you can actually reduce the phase. So, you can add up del V, del VA, del VB and del VC. For this arrangement, it is evident that injected voltage del VA, del VB and del VC are in phase with the line to the neutral voltage VA, VB, VC. So, you can actually have a voltage regulator which can inject the voltage or take out the voltage in the same phase. So, it will add up or decrease, it will add up or decrease by the same amount. And you can have a quadrature voltage regulator. Let us understand how can you make a quadrature. It is very simple, actually all are 120 degree phase shift. It is VA, this is VB and this is VC. If I want to make this voltage which is actually perpendicular to the V, so ultimately you just, this is minus VC and take the resultant of it and scale it. So, actually BC, if you inject BC in phase A, that will be leads to the 90 degree phase shift, same way for the other phases, and that is what it is been done here. Actually this is the VA and this is the del VA, and what happened, you can add this phase here and here, you can add this phase here and here, and so that you can have these 3 voltages. Ultimately you have to see that when you are, it is in a star combination, it is in a delta combinations. So, ultimately it will have a 30 degree phase shift. So, this will lead to the 60 degree phase shift of the voltages, and ultimately you get a voltages at quadratures of the current. So, ultimately A, B, C. So, this is point is A. Similar manner, the arrangement can be made used for the phase angle control. That means the injected voltage del V to have a phase of 90 degree relative to the system voltage, and this is the combination with the line, you will have a 90 degree phase. For relatively small angle adjustment, the resultant angular change is approximately proportional. So, when delta and sin delta is almost same, or that this value change rather. So, then the angular change is proportional to the injected voltage, while the voltage magnitude remains almost constant. So, this value will change. For large angle adjustment, then voltage will change. The magnitude of the system voltage will appreciably increase or decrease. For this reason, it is often referred to as a quadrature boost transformer. Generally, it is enhanced. So, we shall use this term very frequently. QBT arrangement is typically has been used in conventional phase shifting application. Power flow control by phase angle regulator or PAR. So, the optimal loading of the transmission line in practical power system cannot be achieved due to the following reason. Mostly the delta, we have a limitation on the delta on achieved at the prevailing transmission line. For example, when power between the two buses is transmitted over the power lines of different electrical length, it is sometimes difficult to have the same electrical length even though they are coming from the 2 points. Then two buses are inserted whose prevailing phase difference is insufficient to establish the desired power flow. So, one will supply power angle delta minus 1, assume that it is 0, that it is generally reverse, and if it is V0 it will be minus delta 2. So, there you require to have a phase correction, and the two buses inserted prevailing the angle difference is insufficient to establish the desired power flow, because someone will carry more current and someone will carry the less current. In these cases, phase angle regulator or PAR is frequently applied to actually make this their phase voltage angle same. So, thus this is the one line diagram of PUR from the two machine model. This is the supply voltage, in between you have a phase angle regulator, and that will actually change the phase angle by sigma. So, ultimately it will inject with sigma, and thus this is the sending an effective voltage after that phase sigma, and you got a X and you got a R. So, this is the way of representation of PUR. Now, how does it work? Let us understand the phasor of PUR. The effective sending end voltage Vs effective becomes sum of the prevailing sending end and the Vs voltage, and that is sigma is provided by the PUR. So, what happened? Let us assume that this was your initial Vs and this was your initial VR, and you can add or subtract V sigma with that supply voltage, and thus effectively you can make it minus sigma or plus sigma, and ultimately Vx is a case where it is sigma is added, and Vx is the case where sigma is subtracted, and Vx is the case where actually you have the when actually it is uncompensated, V sigma equal to 0. So, from this understanding of the phasor, the basic idea behind the independent angle regulation is to keep the transmitted power at desired level, independent of the prevailing transmission angle delta. In this, power can be kept at the peak value after the angle delta decreases by pi by 2. By controlling the amplitude of quadrature voltage V, so that the effective phase angle sigma minus delta between the sending and the receiving end voltage stays as pi by 2. the PAR, the transmitted power P and the reactive power demands at the receiving line will change in this fashion. So, you had P, that is V square by x sin delta, in this case it becomes delta minus sigma, and the reactive power also changes V square by x 1 minus cos delta minus sigma. The phase angle regulator does not increase the transmittable power of the uncompensated line. Please understand that angle does not increase the value of the P max, but it can shift the P max. So, it was uncompensated line. So, that here it is pi, but you have added sigma, now new power will come at this point, and within the region you know that it can change the maximum power. It makes or keep the power at a maximum value at any delta, that is the advantage. So, you can make the power maximum at even at 30 degree, even at 45 degree, even some other value also. So, this ranges to actually sigma should be less than minus pi by 2 to plus pi by 2, and that is actually the range for sigma. The result shifting P versus delta curve to the right will what will happen. So, you can increase the delay angle. The P versus delta curve can also be shifted to the left side by inserting voltage to the angle regulating in a opposite polarity. So, you can shift to plus sigma voltage this way, you can get this voltage by injecting minus V sigma. Now, let us see the characteristics of the PR. If the angle of the phasor Vs relative to the V sigma is stipulated to be fixed at plus minus 90 degree. So, you have a 90 degree injection, the phase angle regulator becomes quadrature boost. So, QB. So, effective voltage becomes V square plus sigma square. For quadrature boost type angle, the regulator of the transmitted power have this logic V square by x sin delta plus V square by Vx cos delta, and thus this will be the power curve, real power curve, and this is for sigma equal to 1, this is for sigma equal to 0.66, this is for sigma equal to 0.33. In this case voltage also increases because it increases the sending end voltage. So, this is the case, and this is a case for sigma equal to 0. Similarly, this is a case for sigma equal to minus 1, and this is a case of a sigma equal to plus 1. If you make it sigma plus, this curve will shift to the left hand side, and if you make it sigma minus, curve will shift to the right hand side. So, the contrast to the previously investigated shunt and the series compensation scheme, it has a major advantage. The phase angle regulator generally have to handle both real and the reactive power in same manner. So, it has a property that it can handle reactive as well as real power. Consider the two machine system, same thing we have discussed. So, S and R connected by a single transmission with reactance X and the resistor R. The transmitted power P from S to R results in a difference in magnitude between the terminal voltage Vs and Vr, and also a shift in phase angle. The vectorial or the phasor representations of the voltage difference Vi is given by Vs minus Vr. So, we can split this voltage into the we have discussed this VQ model, that we can split this voltage by the Parkes transformation by Vd and Vq in real and the quadrature axis. Thus, it becomes a synchronous model when you actually 3 phase ABC system. From ABC to you have stationary transformation, that is alpha beta, then you feed the PLL theta, and thus you get the TQ and DQ, they are decoupled. So, analyzations is easier. The phasor Vi is normally considered to be composed of the resistive and the inductive voltage drop of Ix and IR. In practice, the power systems are normally connected more than the two machines. So, more than the two machines in parallel in a transmission path, resulting in the one or more circuit loop with the potential of the circulating current flow. So, there might be instantaneous power difference between two lines. So, for this reason there will be a circulating current here. Consider defined system with two parallel transmission line, and since this angle is angle delta 1, so an I1 and I2 will have different. So, for this reason you will have a different current flow. The basic consideration indicate that x by r ratio of these two lines are not equal, then circulating current will flow through the transmission line. This is basically the Wheatstone bridge kind of thing. We shall decompose this both the current, decomposing both the current I1 and I2 in phase and the quadrature, which was I was trying to explain in previous slide. Quadrature component with respect to the sending end voltage Vs. This will see this equation in next slide. So, this is the in phase component for ID1 will be ID1 plus the circulating current in phase with the d axis into R1 and plus this actually reacting component, that is x1 IQ into CQ. Similarly, you will have V1Q. V1Q will be IQ, I1Q plus CQ into R1 plus J ID1 plus ICD into x1. So, there will be a cross component of it. Okay. So, here it will have a real component, this Q with x and D with R, and it will have a cross component Q with R and ID with x. So, similarly, the terms of VD2 and IQ and can be written. So, this will be 2 here. So, for this reason this equation will be as follows, and from this equation it is quite clear that if this ratio x1 R1 and this x2 R2 is same, then ICQ and ICD both will be 0. The case when the series and the difference in the quadrature voltage component are this one V1Q minus V2Q. Let us consider the practical assumption that we know that actually x by r ratio is around 7 or 10. So, this much is the constraint, x1 is much greater than R1 and similarly x2 is much greater than R2. This difference will primarily will maintain the in phase circulating current component of ICQ. Thus, increase in real power in one line and decreasing lower real power in other line. So, you will find that more line will actually flowing to the line 1 and less power is flowing to line 2, and this will be the phasor. This is basically the Vi what we have represented, this is Vs minus Vr, this is basically Vq that you have injected, and ultimately this is Vr and this is Vs. And similarly, what you can do, you can actually have this opposite, for the phasor for the line 2, this is actually VR and this is Vs and this is Vs minus VR, and ultimately CQ will be in this directions, and thus this value of this voltage will be actually more here and this will be this. So, due to that what will happen? So, conduction will take place in different line, different manner. So, for this reason we require to compensate it and we try to make it this value equal, and you see that we have eliminated the component actually the CQ. In case when there is a difference in the phase component of the voltage component VD1 and VD2, the difference will primarily maintain the in phase circulating current component CD, assuming, and we can compensate actually if this VQ and this V1Q and VQ are same, and thus change in reactive current flow will balance, but there will be a difference of the real power flow. We actually come to this point then. In general case, the difference may exist between the both in phase and the quadrature of the voltage component, which will maintain the circulating currents, changing both the real and the reactive power flow balance between the line. This distribution of the real power flow over the interconnection forming the loop circuits can be controlled by PAR. The phase angle regulator inject a quadrature voltage in series, thus it can effectively control the VQ better in series when with the circuit loop resulting the flow of the in phase circulating current. So, it will increase the ID1 and ID2. Flow of the reactive power can be controlled by the voltage regulator. So, PIR can control the current regulator. Voltage regulator introduces a series in phase voltage into the loop and quadrature current is circulated through the loop. Thus, both by operating with the PIR and the VAR, we can regulate the power flow between these two lines. Thank you for your attention. I shall continue with our discussions with the power angle regulator in our next class.